Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. My name is Izzian Wahida binti Zainuddin, representing my group from Polytechnic Sultan Abdul Halim Muazzam Shah. Today, I would like to present our research topic, Eco-Bioplastics Packaging, LDPE or cornstalk powder with coconut oil coupling agent, COCA, influence of coupling agent on mechanical properties. First, we go for the introduction. Biocomposite materials can be broadly defined as composite materials consisting of natural filler and a fossil fuel-based polymer such as polyethylene and polypropylene, or we call as biopolymer. Studies on biocomposite have drawn interest among other researchers, and it has been an active research subject in this decade due to environmental campaign. Most 80% of our daily lives involve the usage of plastic bag, plastic container, and water container because they are made of low-density polyethylene resin. This situation is also common in other fields such as industrial, farming, and automotive, whereby the same plastic of low-density polyethylene being used. There are a lot of industrial and waste materials that are currently being thrown anywhere, and one of them is agricultural biomass waste. Value-added processing would help in agricultural divisions. Our research objectives. First, to study effect of CS loading on tensile properties and morphology of eco-bioplastics packaging, LDPE or CS biocomposites. And the second one is to investigate the effect of coupling agent, coconut oil coupling agent, on CO bioplastics packaging, LDPE or CS biocomposites. Filler and matrix. Cornstalk as filler is selected as the biomass feedstock. Corn is an important crop all around the world. As it is expected, after huge amount of production, huge amount of residue remain. Matrix in this research, low density polyethylene or LDPE. Our research methodology. The low-density polyethylene grade LDF200YZ film extrusion general purpose was supplied by Titan Chemicals Corp. Berhad. The cornstalk was obtained from Kodeang Plantations, Kedah. After cleaned, the cornstalk was crushed and grinded into powder. Our coupling agent used is coconut oil coupling agent. For our research methodology, materials for LDPE is 100 without COCA and also 100 with COCA. CS on PHP unit is 0, 10, 20, 30 and 40 without COCA, and also the same value for COCA. And COCA PHP, we use 3 PHP on LDPE CS with COCA. This table is short formulation of LDPE or CS biocomposites. 3 PHP from with LDPE. First is preparation of filler, which is CS, and then preparation of LDPE or CS biocomposites. Then we go for mechanical testing and morphology analysis, SEM. Results and discussion. Here we have the mechanical properties. First is about the tensile. Figure 1 shows the effect of filler loading on tensile strength of or without COCA and with COCA for LDPE or CS biocomposites. The tensile strength of LDPE or CS biocomposites was decreased when the filler loading increased. It happens because of the weak interfacial adhesion and poor dispersion between filler and polymer matrix. The tensile strength of with COCA LDPE or CS is higher compared to without COCA LDPE or CS biocomposites. This behavior can be attributed to presence of strong interfacial adhesion and better dispersion between filler and polymer matrix with addition of coca. Properties number 2, elongation at break. As figure 2 show that the elongation at break of LDPE or CS biocomposites decreased in the company of filler loading. The elongation at break of both biocomposites show decreasing trend, with CS loading increased due to the presence of coca, which have good dispersion and interfacial region between filler and matrix are formed. At similar filler loading, elongations at break of with coca for LDPE-CS biocomposites lower than with coca biocomposites, and presence of coca shows plasticizer properties of LDPE or CS with coca biocomposites. For the Young modulus, the Young modulus for with coca and with coca for LDPE-CS biocomposites was increasing with the increasing of filler loading as shown in figure 3. The composites with coca in Young modulus have increased when filler loading is increased. It has been identified that modulus of composites can be increased when the filler has higher stiffness than matrix. In the Young modulus, the biocomposites with coca for LDPE or CS is higher than the biocomposites with coca for LDPE CS, even though with similar loading. The results indicate that the efficiency of coca in improving plasticizer of LDPE or CS composites, while the polymer chain mobility inherent by the better filler matrix interaction. The last one is about SEM micrograph. Figure 4 showed SEM micrograph of tensile fracture surface LDPE or CS biocomposites with coca 20 php at magnification 200x. Figure 5, SEM micrograph of tensile fracture surface of LDPE or CS biocomposites with coca at 40 php at magnification 200x. This result shows it seems that both micrographs show filler dispersion and adhesion is better in LDPE matrix. The fiber matrix adhesion was enhanced due to the chemical connections between fiber and matrix supplied by the coca. Therefore, these results proved the compatibility between filler and matrix was considerably can be improved when react to the coca. As the conclusion, the effect of coca as a coupling agent in LDPE or CS biocomposites has increased the tensile strength and elongation at break but decreased Young's modulus. The presence of coca showed better dispersion, wettability of CS in LDPE matrix, and morphology of biocomposites with coca showed ductility behavior. So, as now is about our research. With that, thank you.